In this unit on waves, we will restrict our attention to waves involving a set of particles with mass. In other words, we will leave the subject of electromagnetic waves for later, because photons are massless. With this restriction in mind, the waves we will study will need a set of masses called the medium. Example of medium are the water molecule in a lake, the air in a room, a guitar string clamped at both ends, or a slinky. The main characteristic of a wave is that it is a phenomenon where energy is transported without the medium moving along with the energy. It does not mean that the masses in the medium are not moving. They are, in fact, each oscillating roughly on the spot around a position of equilibrium, while the wave is traveling through the medium. It is through the forces between neighboring masses that the energy is transmitted. Let us start with a one-dimensional wave. One-dimensional because all the vectorial quantities such as the net forces, velocities, and positions will require only one component. Our medium consists of a set of pucks connected to each other via negligible mass springs. Here the red pucks are of equal mass and resting on a frictionless table. I chose this example so that we can visualize the strength of the forces between the pucks with the length of the springs, which are shown in blue. When a spring is not compressed or stretched, the spring does not exert any force on the pucks it is attached to. This medium here is shown with springs with their equilibrium length. When a spring is compressed, its ends exert forces on the puck as shown by the yellow arrows. In that situation, masses attached to that spring would repulse each other. However, a stretched spring exerts forces that would pull the masses towards each other. The magnitude of the force that an ideal spring exerts is proportional to the change in length of the spring from its equilibrium length. I do not want to specify the length of the medium because I do not want to deal with what happens at the boundary to the right just yet. Let us say that the string of pucks and springs is very long. We will set this medium in motion with a piston attached to the left end of the first spring. It would force the spring end to follow a back and forth horizontal motion along the line of the pucks and springs. The piston is the local source of the disturbance, the source of the energy. For comparison purposes, let us first show a medium at equilibrium. We will set the time origin after the piston has given a strong kick to the first puck before it sets into its back and forth motion. At that time, the first puck has a maximum velocity, but it is still basically at the equilibrium position. The green arrow above a puck will represent its velocity. Now that the first puck is moving, it will start compressing the spring to its right. This compressed spring will speed up the second puck, and the first puck will slow down because both springs that are attached to it exerts forces towards the left. After a time delta t, the situation might look like this. The third puck is now in the situation the second puck was previously. It will start moving towards the right and slow down the second puck. The first puck will slow down as well and eventually stop momentarily. The medium might look like this at the time when the first puck stops. After time 2 delta t, both the piston and puck number 2 are creating a force towards the left on the first puck. So the first puck picks up speed towards the left. Puck number 2 eventually stops, and it is the turn of puck number 4 to get the maximum speed. At time 3 delta t, it looks like this. If you keep drawing the situation at each increase of time by delta t, you get these situations at 4 delta t, 5 delta t, 6 delta t, 7 delta t, and finally 8 delta t. I stopped at 8 delta t because if you compare the status of the first puck at t equals 0 to its status at t equals 8 delta t, you can see that they are the same. That puck has returned to its equilibrium position, and it is now moving with the same maximum velocity towards the right. It is ready to repeat the same motion as long as the forcing of the piston supplies the correct displacement of the left end of the first spring. The shortest time that it takes a mass to return to the same state of motion is called the period, and the symbol that we will use is the Greek letter tau. Notice the wavy shape of the positions of the first puck as the wave passes through. As to the other pucks, they have not completed their first cycles yet. You can see from this example how energy can be transported through a medium with the masses in the medium staying very near where they were originally. The leading puck is moving and will transfer its energy to its neighbor in the direction pointing away from the source. Let us see again the state of the medium after one period of wave generation and compare it to what it would look like after a second period of generation, so at time equal to 2 periods. There is a repetition of a pattern, but this time it is in space. The distance between a mass at its equilibrium position moving at maximum speed towards the right and the closest mass with the same motion at the given time is called the wavelength. It could be measured anywhere if the pattern is truly repeated. The preceding presentation of wave generation made use of many untold assumptions and approximations, including the use of the simplest wave pattern, which graphically looks like this. The measurement units on both axes are purposely omitted. We are only interested in the general characteristics of a waveform. This particular graph is not representing the shape of the string of springs and pucks in space. The x values of the red dots on this graph are how far horizontally each of the equilibrium positions of the first 17 pucks involved in the wave are from the equilibrium position of the first puck. The y values are the horizontal components of displacement of each puck from its own equilibrium position. They are not vertical component of displacement. An horizontal component of displacement of 0 is when a puck is at its equilibrium position. A positive horizontal component of displacement is when the puck is located to the right of its equilibrium position, and a negative horizontal component of displacement is when the puck is to the left of its equilibrium position. The orange curve that links the red dots is the basic wave function that was used as a model for this presentation. Mathematically, it is called a sinusoidal function. Its main feature is having constant maximum values and minimum values. The difference between the maximum value and the minimum value is defined as being twice the amplitude of the wave. The variable name for the amplitude will be capital A. Here is a more general definition for the amplitude, because the waves we will study will not necessarily have horizontally moving masses or have unit of measurements like centimeter or millimeter. Example of physical quantities that could have wave-like behavior are density and pressure. The wave traveling along the string of springs and pucks that we have just studied is a longitudinal wave. Another example of a longitudinal wave is a sound wave. The definition of a longitudinal wave and the characteristics of a sound wave will be the subject of the next installment.